So the previous class we were discussing on what is Z transforms, what is the necessity of the Z transforms, what are the applications of Z transforms, and we had discussed the Z transforms of few standard functions, namely k raised to n, 1, cos n theta, sin n theta, what is the Z transform of n, n square, n cube, so on. And also we had discussed about the linearity property for the Z transforms, and also we had discussed on the damping rule. Now let us discuss the Z transforms of hyperbolic functions. In this class I shall be discussing only about the hyperbolic function of cos n theta, and sin hyperbolic function I shall leave it for you as homework. So let us start finding out what is the Z transforms of the hyperbolic function. That is, we are supposed to find Z transform of cos hyperbolic n theta. Now to find out the Z transform of cos hyperbolic n theta, I shall be making use of the damping rule which you people had studied in the previous class. That is, if you remember, damping rule stated that if Z transform of un is equal to u bar of z, then Z transform of a raised to minus n un is given by u bar of az, and Z transform of a raised to n un is given by u bar of z by a. We had also discussed few examples wherein we had made use of the damping rule. So let me make use of the damping rule on this and then find out the Z transform of the cos hyperbolic function n theta. So we know that cos hyperbolic n theta is given as e raised to n theta plus e raised to minus n theta divided by 2, the basic definition. And if I take the Z transforms on this, this will be Z transform of cos hyperbolic n theta equal to half times the Z transform of e raised to n theta plus e raised to minus n theta. That is, by making use of the linearity property of the Z transforms. So furthermore, now make a note of this step. Here I take this as Z transform of this hyperbolic function is equal to half times, make a note of this, Z transform of e raised to n theta into 1 plus Z transform of e raised to minus n theta into 1. So now this can be written as half times Z transform of e raised to minus theta times raised to minus n into 1 plus Z transform of e raised to theta raised to minus n into 1. That is, if you can just look onto this, this will be of the form Z transform of a raised to minus n into some function, say un. That is of the form a raised to minus n un. So by the damping rule, we know that this is nothing but u bar of a into z. So this will be equal to half times. We know that the Z transform of 1 is nothing but z by z minus 1, and you can see that e raised to minus theta is raised to minus n. So by the damping rule, here z gets multiplied with the function a. Here we have the function as e raised to minus theta. So this becomes z into e raised to minus theta. Again this z becomes z into e raised to minus theta minus 1. This is by making use of the damping rule. Plus similarly, you can see that the Z transform of 1 here is z by z minus 1, and you can see e raised to minus theta raised to minus n is multiplied with 1. So by making use of the damping rule, here z gets now associated with e raised to theta. Hope so this step is clear. We have made use of the damping rule for this. Now the next step is to just simplify this. That will be half times. Now I'll go for simplifying this. That is z e raised to minus theta times z e raised to theta minus 1 plus z e raised to theta times z e raised to minus theta minus 1 whole divided by z e raised to minus theta minus 1 into z e raised to theta minus 1. I am repeating this again. Here I have made use of the linearity property of the Z transform, and for this particular step I have made use of the damping rule, which says Z transform of A raised to minus NUN will have a function associated as U bar of A into Z. So here you can see that A, instead of A I have got it as e raised to minus theta. So all your Z's are multiplied with e raised to minus theta here and e raised to theta in this particular part. And then we have gone for the simplification. So to proceed further with this, to continue, I'll be continuing over here. So this will be equal to half times. Now let us go for the simplification. That is z e raised to minus theta into z e raised to theta will be equal to z square, because obviously we know e raised to minus theta into e raised to theta will give us e raised to 0, which is 1. Again z into e raised to minus theta minus 1 becomes z e raised to minus theta, and furthermore the next one here z into e raised to theta into z e raised to minus theta, z into z is z square, e raised to minus theta into e raised to minus theta will give us plus 1. So we are left with plus z square, and last one is z e raised to minus theta, e raised to theta into minus 1, which is minus z e raised to theta divided by, so let us multiply that. The denominator we get it as z square into e raised to minus theta into e raised to theta, which is plus 1, and minus z e raised to minus theta, again minus z e raised to theta plus 1. So this is just a simple multiplication what we have done in the simplification. And then proceeding further, I have got z square into z square plus z square, which is 2z square, and out of these two you can see that minus z is a common, so I'll be left with e raised to minus theta plus e raised to theta divided by z square. Again in these two terms you can see that minus z is common, we will be left with e raised to minus theta plus e raised to theta plus 1. Hope so this thing is clear. Now let me make some small changes here so that I get it in the standard form. That is, we know e raised to minus theta plus e raised to theta divided by 2 is cos hyperbolic theta, right? So what I do is, to bring it to the cos hyperbolic term, I shall multiply and divide this term by 2 and similarly this term by 2. That is, I'll get this as half times 2z square minus 2 into e raised to minus theta plus e raised to theta divided by 2. You can check on this. Here I have just multiplied by 2 and have divided by 2. So this again divided by z square minus 2, that is z, into 2 times e raised to minus theta plus e raised to theta divided by 2 plus 1. Now proceeding and making use of this particular result, I'll be getting the z transform of the hyperbolic function cos hyperbolic n theta to be equal to, here this will be half times 2z square minus 2. By making use of this definition of the hyperbolic function, this will be cos hyperbolic theta divided by z square minus 2z cos hyperbolic theta plus 1. These two, I have used the definition of the hyperbolic function, and then here you can see that 2 are common in the numerator, so this will be half times 2 times of z square minus cos hyperbolic theta divided by z square minus 2z hyperbolic function theta plus 1. So you can see that these 2's in the numerator and the denominator cancel each other. Therefore, the result what we have for the hyperbolic function of cos n theta is equal to z square minus cos hyperbolic theta divided by z square minus 2z cos hyperbolic theta plus 1. So this is how we find out the z transforms of the hyperbolic functions. You have for the cos hyperbolic function and the sine, I have derived the z transforms for the cos hyperbolic function in theta, and sine will be left as homework for you to do. Here the only thing you have to be careful about is how to make use of the damping rule. Once the damping rule is put on correctly, you can go for the simplification, and this is how we obtain the z transforms of the hyperbolic functions. Now, once we have done with the hyperbolic function, the z transforms, we shall now discuss on few of the important properties which are associated with the z transforms. So you have shifting property. So today I shall be discussing on the shifting property, say the left shifting property and the right shifting property. So let us start discussing on the shifting property. So to start off with, I shall discuss today on the right shifting property. So as I have told you, please be careful about how to make use of the damping rule. So yes, so under the shifting rule, we shall be discussing first on right shifting rule. Shifting rule, the first thing we are going to discuss is the right shifting rule. Right shifting rule. Under the right shifting rule, okay, the statement goes as, if z transform of un is given as u bar of z, then z transform of u n minus k, okay, be careful, here it is u n minus k equal to z raised to minus k u bar of z. Now the proof for this is very simple. You are supposed to remember the basic definition of the z transform. You know that z transform of un is given by summation of un z raised to minus n ranging from 0 to infinity. And while we were defining the z transforms, we had also told that and un will be equal to 0, okay, for n less than 0. This was the definition what we had talked about when we had defined the z transform. So here what I want is z transform of un minus k. So this will be equal to summation of un minus k z raised to minus n, and n will be ranging from k to infinity. The reason is because if at all I start by taking k value, n value as 0, you see that I get a negative value for which the un value is 0, and if I take n as 1, n as 2, so on. So clearly the definition here should give for k greater than 0. K cannot be a positive. K is taken as a negative, this becomes un plus k. So I take n is equal to k to infinity. Hope so this is clear why we have not taken from 0 to infinity, and because this is defined, un is defined from for the positive values un, or else un is taking the value of 0 for the negative terms, that is whenever n is less than 0 because of the definition. Okay, so let me write it as this is because un will be equal to 0 for n less than 0, that is un minus k will be equal to 0 for n taking the value of 0, 1, 2, so on till k minus 1. Okay, I hope so I have made this thing clear for you, why this is taking the range from n is equal to k to infinity. If I take n as 0, here if I take n as 0, you get u, negative value, right? So for negative n value, un is 0. If I take 2, again you can see that n is less than 0, then un will be taking the value as 0. So on till k minus 1. So if I take this as k minus 1, still I'll be having un, and where n is less than 0. So I can start only from u0. So if you can see that when n is taking the value of k, this becomes uk minus k, which is u0. Hence we are having the range from n is equal to k to infinity. Hope so this step here is clear. That is, I have to start from u0. For all un values for n less than 0 are 0, hence we are starting from taking n is equal to k. So the next step here is z transform of u, n minus k is equal to, now just start giving the values of n as k. So if I replace k as 0, n, I'll replace this n by k, I'll get this as uk minus k, which is 0, and z, n is taking the value of k, so this becomes u0 z raised to minus k. And then the next value of n will be k plus 1. So this will be u, this is k plus 1 minus 1, so this is u1 z raised to minus k plus 1. That is, we have started by taking the values of n as k, k plus 1, k plus 2, so on. So the next term what I have for k is n is k plus 2. So if I replace n as k plus 2, this is k plus 2 minus k, which is u2. So u2 z raised to minus k plus 2 plus so on. Now the things are easier here. So this is u0 z raised to minus k plus u1. See, I can split it as u z raised to minus k into z raised to minus 1, of course, plus u2 into z raised to minus k into z raised to minus 2 plus so on. Now out of this you can see that z raised to minus k can be taken out. So if I take z raised to minus k out, I'll be left with u0. Here z raised to minus k is taken out, plus u1 z raised to minus 1, because z raised to minus k is taken common out there, plus u2 z raised to minus 2 plus so on. So if you can look onto this, that is z transform of u n minus k, if you can see the right hand side part of it, you can see that this is nothing but z raised to minus k, and this is nothing but the summation of un into z raised to minus n ranging from 0 to infinity. Just check, if I can replace the value of n as 0, I get the first term u0. If I replace n as 1, I get the first term u1 z raised to minus 1, so on. But what is this summation of un z raised to minus n when n is ranging between 0 to infinity is nothing but z transform of un. And we very well know that z transform of un is also denoted as u bar of z. So this is nothing but u bar of z. That is how we have proved that z transform of un minus k is z raised to minus k u bar of z. So this is what the right shifting property says. You have to be careful with this very step, why we have started from taking n as k. Okay, the reason is that by the definition of the z transforms, un will take the value of 0 whenever n is less than 0. That is why for all these values of n 1, 2, 3, so on till k minus 1, un minus k will be taking the value as 0. So the next term we have to start for n is k. I hope so this is clear. Now let us discuss on the left shifting property or the left shifting rule. So the next one is left shifting property. left shifting property is very much, yeah. What does the statement say? The statement says that if u bar of z, or I'll say that if z transform of un is u bar of z, then z transform of un plus k, see, for the right shifting property we had un minus k, here it is un plus k is equal to z raised to k times u bar of z minus u naught minus u1 z raised to minus 1 minus u2 z raised to minus 2 minus so on minus u k minus 1 z raised to minus times k minus 1. So this is what the left shifting property says, and the proof for this is very simple. Let us discuss on the proof of this. Yes, the proof goes as usual. Let us just write the basic definition of the Z transforms. What does the basic definition of the Z transform say? Proof Z transform of un is nothing but summation of un z raised to minus n ranging from 0 to infinity. This is what we have, the basic definition for Z transform. And now let us start. What we want is Z transform of un plus k. So this will be equal to summation un plus k z raised to minus 1, so minus n ranging from 0 to infinity. Okay. Now the next step, just make a note of this. This will be equal to summation un plus k. Okay. This is z minus n as usual into z raised to minus k into z raised to k. What I have done is just multiplied and divided by z raised to k. The reason is I want this z raised to k here. So let me make some small change. That is, I'll just multiply and divide by z raised to k. That is z raised to minus k into z raised to k. Obviously, it's going to give me 1. So I'm not basically changing the definition. Okay. So again, the range is obviously between 0 to infinity. So now you can see that the summation is on n and it has got anything to do with the values of k. So z raised to k can be taken outside the summation. So n is equal to 0 to infinity, u raised to n plus k. Now what is remaining is z raised to minus n into z raised to minus k. Obviously this will be z raised to minus n plus k, right? This is an important step. Rest of the things will just fall in place with a normal substitution. So z transform of un plus k will now be equal to z raised to k. Now let us start giving the values of n as 0, 1, 2, 3 because I have already told you that the z transforms are based on positive integer values. So let us start by write the series by making use of n value as a 0. So if I take n value as 0, I'll get this is uk z raised to minus k. Okay, and then n value as 1, I'll get this is u k plus 1 z raised to minus k plus 1. Similarly, if I can give the n value as a 2 because 0, 1 and 2. So u k plus 2 z raised to minus k plus 2 plus so on. This is how we have got the expansion. So this is z raised to k. Now look on to this step. I'll just add few terms and subtract those terms. That is, I go for u naught plus u1 z raised to minus 1 plus u2 z raised to minus 2 plus so on plus uk minus 1 z raised to minus k minus 1. These were the terms which are not present, right? Now since these are not present, I've added it, and since I've added it, I have to even subtract them. So I'll go for minus u naught minus u1 z raised to 1 plus u2 z raised to minus 2 plus so on uk minus 1 z raised to minus k minus 1. these are the terms what I have added, and the same terms have been subtracted, and there are these terms, of course, which we are supposed to write. So the terms which were there were uk z raised to minus k plus uk plus 1 z raised to minus k minus 1 plus uk plus 2 z raised to minus of k plus 2 plus goes on, right? So whatever the terms were there in the previous step, for those terms I have added few terms and the same terms I have subtracted. So basically it is not going to change the given equation or the terms. Z raised to k is equal to, now if you can look on to these terms here, what do we have? u0, u1 z raised to minus 1, u2 z raised to minus 2, uk minus 1, and then uk plus 1, uk plus 2, this is just going on. That is, I can write this whole term as summation un z raised to n ranging from 0 to infinity. If you want, you can just cross check. When I replace n value as 0, I get u0. When I replace next value of n as 1, I get u1 z raised to minus 1. When I replace n as 2, I get u2 z raised to minus 2, so on. If I replace n as k, I get uk z raised to minus k, and this is how this goes on. So this whole term here, whatever I have written in the flower brackets, is nothing but the summation of un z raised to minus n, and these terms are still left, that is minus u0 minus u1 z raised to minus 1 plus minus, these are all minus here, so minus u2 z raised to minus 2 minus so on minus uk minus 1 z raised to minus k minus 1. And we very well know that the summation of un z raised to minus n can obviously be denoted as u bar of z. So I can write this as z raised to k, and this is nothing but u bar of z minus u0 minus u1 z raised to minus 1 minus u2 z raised to minus 2 minus so on uk minus 1 z raised to minus k minus 1. So this is what we were required to find, that is z transform of un plus k is, this is what we have got as z raised to k u bar of z minus u0 minus u1 so on till u k minus 1 z raised to minus of k minus 1. This is how the left shifting property goes. Two important steps here to remember. Here multiply and divide by z raised to k, and later on you are supposed to add few terms and subtract few terms. These are the two important steps which you are supposed to know in this particular proof, right? So now this left shifting property is used later on while we will be solving the difference equations. So also let us make a note from this shifting rule, that is z transform of un plus 1 in particular. So here we have got z transform of n plus k. This is z transform of un plus k. So if I want for un plus 1, that is here k will be taking the value as 1. So I shall have this as z raised to k is 1, so z raised to 1 u bar of z minus u0, right? Because k value is 1 here, k value is 1. And then see, the last term is k, and k value is 1, so I cannot go for the negative value. And then we go for z transform of un plus 2, that is k is taking the value of 2, so z square u bar of z minus u0 minus u1 z raised to minus 1, that is k is taking the value as 2. So z raised to 2 u bar of z minus u0, and k is taking the value of 2, so minus u, 2 minus 1 is 1, So this becomes u1 z raised to minus of 2 minus 1, which is 1. So this is u1 z raised to minus 1. This is how we have got. On similar way, I can write z transform of un plus 3 to be equal to z cube u bar of z minus u naught minus u1 z raised to minus 1 minus u2 z raised to minus 2. These are few of the important transforms, left shifting property which we'll be using while solving the difference equations. So yeah, let us go for a problem on this shifting rule. Okay, a very simple shifting rule property problems. Yes. So the problem basically says show that Z transform of, so it says show that Z transform of 1 by n factorial is equal to e raised to 1 by z, and hence find first one Z transform of 1 by n plus 1 factorial, and second one Z transform of 1 by n plus 2 factorial. Okay, yes. Now let us go for the solution of this. Very first thing is we are supposed to show that Z transform of 1 by n factorial is nothing but e raised to 1 by z. So let me go for the basic definition. What is the basic definition of Z transform? Say Z transform of un is nothing but summation un z raised to minus n ranging from 0 to infinity. What I want is Z transform of 1 by n factorial. So this will be summation 1 by n factorial, n ranging from 0 to infinity, z raised to minus n. Now just go on giving the values of discrete values of n, positive. So 1 by, here n starts from 0, so 1 by 0 factorial, we know 0 factorial is 1. So this is 1 by 1, z raised to 0 is 1. So obviously this value is 1. Plus, go for n is equal to 1. I have this is 1 by 1 factorial, z raised to minus 1. Next value of n is 2. 1 by 2 factorial, z raised to minus 2. Plus 1 by 3 factorial, z raised to minus 3. Plus so on. This is how this proceeds. Now, if you remember, what is e raised to x basically? E raised to x is nothing but 1 plus 1 by 1 factorial into x, which is nothing but x by 1 factorial, plus 1 by 2 factorial into x square, plus 1 by 3 factorial into x cube, plus so on. This is what we have, the expansion of e raised to xf. Now if you can compare these two, you can see that this is nothing but, that is, wherever we have taken it as x, here I have got it as z raised to minus 1. So this will be nothing but e raised to z raised to minus 1, or z raised to minus 1 is nothing but e raised to 1 by z. Okay. So let me make this still more clear. That is furthermore, I can write this as z transform of 1 by n factorial as 1 plus 1 by z by 1 factorial, right? Plus 1 by z square by 2 factorial, because z raised to minus 2 is nothing but 1 by z square, plus 1 by z cube by 3 factorial, plus so on. Now see, the comparing is easy. So you can see that instead of x everywhere, you have got it as 1 by x. So this is nothing but e raised to 1 by z. So z transform of 1 by n factorial, we have got it as e raised to 1 by z. So we have used e raised to x expansion, and then we have found out the z transform of 1 by n factorial is nothing but e raised to 1 by z. Now the second part of the question is, we are also supposed to find what is z transform of 1 by n plus 1 factorial. Yes, To find out this, I am supposed to make use of the left shifting property, which we have just discussed. So the second part is we are supposed to find Z transform of n plus 1 factorial. Yeah. Just now we had studied that Z transform of u n plus 1 is given by Z times u bar of Z minus u naught. By the left shifting property, we had also discussed on the note. I have used the first note on it. Now what I want is Z transform of 1 by n plus 1 factorial, right? So by making use of this, see, what I have is Z transform of un, which is nothing but Z transform of 1 by n factorial, and I found out it to be equal to e raised to 1 by z. Now Z transform of un plus 1 is nothing but Z transform of 1 by n plus 1 factorial. That is why I have written it. So this will be equal to Z times u bar of Z. What is u bar of Z? U bar of Z is nothing but Z transform of un. And we have found out that the Z transform of un is e raised to 1 by z. And the next thing is we want u naught. What is un basically? Un is nothing but 1 by n factorial. Un here is nothing but 1 by n factorial. So what will be u naught? U naught will be 1 by 0 factorial, and we know that the value of 0 factorial is 1. Hence u naught value will be equal to 1. As simple as that. What I have used here is the left shifting property. Z transform of un plus 1 is z into u bar of z minus u naught. Now what is u bar of z? U bar of z is nothing but the Z transform of un, and we have obtained that the Z transform of un is nothing but e raised to 1 by z. So u bar of z I have written it as e raised to 1 by z by making use of this, which we have previously finished. And then I wanted u naught. Very well, we know that un is 1 by n factorial. Yes, un is nothing but 1 by n factorial. So if I take u naught, that is n is taking the value of 0, this becomes 1 by 0 factorial, and 0 factorial is 1. So this is how we have got the Z transform of 1 by n plus 1 factorial. Next thing is Z transform of 1 by n plus 2 factorial. This also is in the similar fashion, that is by the left shifting property, Z transform of, okay, I'll write it in that end. Right, yeah. So Z transform of un plus 2 we have obtained as z square u bar of z minus u naught minus u1 z raised to minus 1. As simple, that is z square. Yes, what is your u bar of z? Your u bar of z is nothing but z transform of un, and un is nothing but 1 by n factorial. Therefore, the z transform of 1 by n factorial is e raised to 1 by z, which is u bar of z. So let me just replace it as e raised to 1 by z, and u naught value we have just found out, u naught value is 1, and then what we want is u1 value. Obviously u1 will be 1 by 1 factorial, which is nothing but 1. So this is un is 1 into z raised to minus 1. So this is how we have obtained z transform of 1 by n plus 2 factorial. So this sums up the problem on the left shifting property. Now the next thing what we are going to discuss are two theorems, that is the initial value theorem and the final value theorem. Now to start off, let me start with the initial value theorem first. Okay, so the theorem here is simple. Let us discuss on initial value theorem. So hope so this problem is clear for you. Now, yes, what does the statement say for the initial value theorem is, if the z transform of un is u bar of z, then the limit of u bar of z as z tends to infinity is u naught. You can furthermore proceed with how to find out u1, u2, etc. Let us discuss it. So, the initial value theorem. The initial value theorem. How does the statement go? Right? So, the theorem goes as, the statement of the theorem goes as, if z transform of un is equal to u bar of z, then limit of un as z tends to infinity, this is u bar of z, yes, obviously, because z is tending towards infinity, is equal to u naught. Okay, so the statement says that if z transform of un is u bar of z, then limit of u bar of z as z is tending towards infinity will be taking the value which is equal to u naught. Now, the proof is very simple. Let us start with simple. Let us go for the definition of z transform. The z transform of un is summation of un z raised to minus n is ranging from 0 to infinity. This is what we have, right? And what is this? This is also denoted as u bar of z, right? So, let me continue with this. So, now u bar of z, which is nothing but z transform of un, let me write it in terms of the expansion, that is n is taking the value of 0, 1, 2, 3, etc. So, this becomes u naught plus u1 z raised to minus 1 plus u2 z raised to minus 2 plus u3 z raised to minus 3 plus so on, or u bar of z, I'll write it as u naught plus u1, okay, z raised to minus 1 is nothing but 1 by z, so u1 by z, right, and u2 z raised to minus 2 is nothing but 1 by z square, so this is z square plus u3 z raised to 3 plus so on. Now, what I want is the limit of as z is tending towards infinity. So, let me take the limits. So, this will be limit of z tending towards infinity u bar of z. So, this will be equal to limit of z tending to infinity u naught plus u1 by z plus u2 by z square plus u cube by z cube plus so on. Now, left hand side will remain as it is, limit of z tends to infinity u bar of z. Now, on the right hand side you can see that the z is tending towards infinity and the first term has got no z with it. So, you have this as u naught as usual plus, now u1 z is tending towards infinity, 1 by infinity you know is the value as 0. Similarly, this term will be taking value as 0, this term is a 0, so on. So, all the further terms are taking the values as zeros, right? So, what are we left with? We are left with limit of u bar of z as z tends to infinity is equal to u naught. Now, u naught is left here because see that u naught is not containing any z with it. This is how we have got the proof for the initial value theorem. Now, if you want to, we can further find out how u1 can be written, right? Now, let me go for this particular part, okay? With this we end the proof for it. Now, let me go find out what can be u1. So, if I go for this definition, I'll get this as u bar of z minus u naught will be equal to u1 by z, okay? So, let me make this easier for you. Let me talk about this particular part. From this I get it as u bar of z minus u naught is equal to u1 by z plus u2 by z square plus u cube by z cube plus so on, right? I have just shifted this u naught from right hand side to the left hand side. Now, let me take z common. So, if I take z common, if I take 1 by z common, so the z shifts, so we will be left with z times u bar of z equal to u1 because 1 by z was taken common and that z is shifted to the left hand side. Here I'll be left with u2 by z plus u cube by z square plus so on. Hope so this is clear for you. I had taken 1 by z common and that z is shifted for the left side. Now again, if I can take the limit on this, right? So limit of z tends to infinity, z times u bar of z minus u naught will be equal to, now u1 has got no term of z, so this is u1, and limit of z tending to infinity, so u2 and z tending to infinity, this term becomes 0, similarly this term becomes 0, so this is how we have got u1 to be equal to limit of z tends to infinity, z times u bar of z minus u naught. Similarly, you can find out what is u2, u3, etc. So now let us discuss on initial value theorem. Okay. Now, yeah. So next thing what we are going to discuss is the final value theorem. Let me discuss 1 or 2 steps on this, and the next class we shall discuss on complete final value theorem, and then we will be learning about the inverse Z transforms and then how to solve by making use of solve the difference equations by making use of Z transforms. Yes. So how does the statement of the final value theorem go? The final value theorem, we shall discuss about final value theorem in the next class. Basically, to find the final value theorem proof, we again make use of the Z transforms basic definition, and then we shall be proving the final value theorem. Final value theorem we shall discuss in the next class. The inverse of the Z transforms and how to solve the difference equations is what we will be doing in the next class. Thank you.